were to ask better questions of our phones? Like, what if a phone could see in the dark? Or what if a phone could test if water is clean? What if you could share the best parts of your phone with your friends, with your family, or perhaps not in the Bay Area, but with a village? What if a phone could? So we think that a phone should. And so Project Ara is about opening the mobile hardware ecosystem. It's about making the creation of mobile hardware more like the creation of mobile apps by lowering the barrier to entry, by increasing the number of participants in the ecosystem, by enabling developers to sell directly to the consumer rather than having to go through an OEM, and by giving developers new hardware design tools that are free and that make hardware design more like software development. Now, in addition to the what questions, we also wanted to ask why. Why do it? Why does it matter? And so I find this photo to be a particularly poignant reminder. It's titled Signal. It's by John Stenmeyer from National Geographic, and it depicts migrant workers in Djibouti trying to catch a cell phone signal from neighboring Somalia. And I think it's a stark reminder of the fact that, yes, there's 1.5 billion smartphones out in the world, but there are also 6 billion people who are not connected to the mobile internet. And delivering the mobile internet to those people could in fact be world-changing. So we asked ourselves, how would we do that? What would it take to deliver the mobile internet to the next 5 billion? Now, a single device, this is almost impossible to do with a single device. There's a diversity of wants, needs, likes, and budgets that's insurmountable. So we looked for inspiration from other industries. First, we looked at automotive. Of course, in the early days of automotive, there's the infamous Henry Ford quote that says that you can have it in any color so long as it's black. It's good enough for everyone. But as the industry matured, a power user base emerged that took customization to all sorts of extremes. And what's depicted there is the Local Motors Rally Fighter, which is a community-designed and community-built vehicle. Now, a modern mass-market car today has about 30% of its value that's tied up in user-customizable options. So these are both functional options, like engine size, as well as aesthetic choices, like upholstery and exterior. It wasn't so long ago, maybe a year or two ago, that when you bought a new smartphone, your choice was pretty much the same as the early Ford Model T. Would you like it in black? Would you like it in white? So last summer, summer of 2013, we undertook a project to create an open, hackable phone. We were at Motorola at the time, and it was called the Moto Maker phone. We basically attached an Arduino board, we unlocked, rooted the phone, and pinned out some of the data buses to the Arduino. Got in a truck and went around the United States, visited 12 universities, maker fairs, and held makeathons. So 48-hour format, and had some of the best and brightest design and engineering students in the country see what they could do with open mobile hardware. And the diversity of things that emerged was really an exciting proof point for us. We saw things like a glove that could interpret ASL and convert it into text messages. We saw students using a phone and the gyro and accelerometer sensor suite in the phone attached to a skateboard to monitor the quality of the terrain that the skateboard is traversing and share that with other skateboarders in the area via Google Maps. We saw an optometric examination suite as a module that attached to your phone and did a series of exams for your eyes. So to us, that was really a demonstration and an eye-opening experience of the kinds of things that emerge if you create an open ecosystem. So we wanted to do better than cars. We wanted to create a modular platform around mobile. And in order to do that, we thought that it would be useful to look at some examples from history of successful platforms. I personally am an aerospace engineer, so I'm partial to the example of the B-52, the Stratofortress, which is a strategic bomber that entered service with the US Air Force in the 1950s. Remarkably, the B-52 is not only still in operation, but is estimated to serve with the United States Air Force for another 20 to 25 years. Now, by the time this airplane retires, there will not be a single component, from rivet to integrated circuit, that was there in the original 1955 aircraft, yet morphologically, it will still be recognizably a B-52. The different pieces of the aircraft will have gone through a varying number of generations of changes, 1 or 2 generations on the structural side, and 5, 6, 7, 8 generations on the battle management system and the electronics. Yet it retains the overall recognizable feature of being a B-52 and being a remarkably flexible and upgradable platform. Now, closer to the mobile space, perhaps, is the IBM System 360. Introduced in the mid-1960s, a typical core configuration was about $100,000 in then-year dollars. A typical installed configuration, also in then-year dollars, was about $5.5 million. What allowed for this 50x increase in size of the peripheral ecosystem vis-a-vis the actual system core? And what allowed it was the fact that it was the first open modular platform. Now, you might argue that in mobile, we have modularity today. There's a USB port, there's an audio jack, there's Bluetooth, there's Wi-Fi. I can add all sorts of modules to my phone, and there are some, in fact, some examples out there. The Square credit card reader, there are chargers, there are headsets, and other sorts of things. Yet the size of the modular peripheral, so to speak, ecosystem around smartphones today is about 7% of the overall smartphone market. Now compare that to the 50x that was realized for the IBM System 360. And so you might ask yourself, well, why is that? What is it about that makes it kind of anemic? And the hypothesis that I'd like to proffer for you is that unlike the IBM System 360, and perhaps more like the B-52 example, the phone is a physically constrained. The actual exterior of the phone is a heavily physically constrained object. And what you have today is this Christmas tree of stuff that hangs off of your phone that attaches via a variety of wires. And if it's wireless, then it has a power charging tail that you have to drag behind it. So it is not an integrated monolithic whole. And I use the word monolithic specifically in reference to a modular design, in sort of in stark juxtaposition to it. So we asked ourselves the question, could you make a modular device that is both delightful, but is also expressive of users' functional preferences and of their aesthetic preferences, because those preferences are so diverse? And so we also set ourselves quantitative target with respect to each goal. And in the case of this particular goal, we wanted to try and attain an order of magnitude increase in the subjective user perceived value of the device from the customization features, from the functional and aesthetic customization features that you can get from making it modular. We also wanted to make it affordable yet aspirational. Affordable means that it is accessible to the feature phone crossover price point, so that translates to a bill of material cost in the $50 to $100 range. Not necessarily price, but at least bill of materials cost. Yet we also wanted to make it aspirational. We wanted users to aspire to a phone that might be a $1,000 device, that might have an extraordinary camera, a high-resolution display, personal medical diagnostics, and other kinds of things. So we wanted to be able to configure an order of magnitude variance in bill of materials cost off of the same platform. I mentioned that we also wanted to make hardware development more like software development. And the metrics associated with that are that we wanted to have hundreds of developers. Ultimately, we aspire to a developer ecosystem around Ara that rivals the Android app developer ecosystem, but we'll settle for a couple hundred for now. We also wanted to give developers a new set of tools that would allow them to create a module that in essence is correct by design, so that there is only one build spiral required. In essence, this is similar to what VLSI design has come to in recent years, where the first chip out of the foundry is usually correct by construction, instead of having 4 to 5 build spirals as is typical in mobile today. And lastly, we wanted to exploit a DARPA-style project structure, and I'll explain exactly what that means. But in essence, this comes down to the fact that from idea to market pilot, we constrain ourselves and hold ourselves to 24 months. So let me talk a little bit more about this DARPA development model that we're employing on Project Ara. If you notice, I come from not just Google, but Google ATEP. It's the Advanced Technologies and Projects Group. It's headed by Regina Dugan, my boss. who was President Obama's first appointee as DARPA director. DARPA is the Defense Advanced Research Projects Agency. For those of you who are unfamiliar, it is the agency that originally created ARPANET, the Global Positioning System, radar stealth technologies, a variety of rocket engines, and other iconic innovations. And there are three things that are key to the DARPA model of innovation and that we're trying to exploit in the private sector in ATAP. And those are projects, people, and partners. On the project side, as I mentioned, one of the things is we try to constrain projects to a finite duration. And projects live in what's called Pasteur's quadrant. And this is a construct from a political scientist named Don Stokes. And he basically thinks of mapped innovation into 4 different quadrants. On the horizontal axis is consideration of use, meaning how applied or what is the utilitarian application of the technology. On the vertical axis is the quest for fundamental understanding, or basic research. And so on the quadrant on the vertical axis is called Bohr's quadrant. It's pure basic research. It's doing research for the sake of gaining scientific insight and nothing more. On the horizontal axis, you see Edison's quadrant, which is pure applied research. It's wanting to put something into the stream of commerce and solve some everyday problem. In the upper right, however, is Pasteur's quadrant. And Pasteur's quadrant is use-inspired basic research. In essence, taking fundamental insight, breakthrough basic innovation, but tethering it to a moonshot practical application that is extraordinarily compelling. And so that's where ATAP projects live, in Pasteur's quadrant. We also have an interesting philosophy with respect to people. We bring people in for a very short period of time, and we have a very, very small team that operates within Google. So on Project Ara, for instance, which is a sizable effort to make in essence, a smartphone, we have 5 Googlers working on the project. Yet we have 350 or more people, and it fluctuates from week to week, outside of Google, across partner organizations that include large companies like Toshiba, small companies that you've probably never heard of, and other partner organizations like universities and actually Linaro, and I'll talk more a little bit about that as well. And the reason that we use external partners is because it lets us turn on a dime, and it lets us capture world's best-in-class talent, people that I could never recruit to pack up, move to Mountain View, and work for Google full-time. So back to what it is that we're developing. The best metaphor that I have been able to come up with for what we're after, the level of customization and the level of cultural ubiquity, is food. And so, in fact, the inspiration for the industrial design of Project Ara came from the Japanese lunchbox, the bento box. The bento box is kind of a remarkable object. What it allows the chef to do is to combine a wide assortment of very disparate dishes and tastes and flavors and ingredients that are disparate both visually and in terms of their flavors, and combine them into a coherent meal. A meal that's made cohesive by something that's very, very simple, that's very, very elegant, and that celebrates both the diversity and the uniformity of what's being provided to the consumer. And so that's where the Ara industrial design came from. Instead of concealing the modularity, we wanted to celebrate the modularity of the device. We also wanted to overcome the preconceived notion that most consumers have, that modular equals brick-like or block-like or Lego-like. We wanted to make the modules sleek and watertight and pebble-like in appearance. So we harnessed 2 technologies in service of this objective. The first one is trying to not have mechanical latches or mechanical connectors. Try and make the module completely, as I said, watertight and pebble-like. This is an electropermanent magnet. An electropermanent magnet is actually a decades-old technology that's used in industrial crane applications that we miniaturized from something that can lift a car to something that can lift something about the size of a small kitten, about 30 newtons of force. An electropermanent magnet is is a hybrid between an electromagnet and a permanent magnet. It has an on state and an off state. It can switch between those states with a short current pulse, but is actually a passive component in both of those states. The second technology that we harnessed in service of our industrial design vision was that of contactless data interconnects. This was the trade space that we explored, and actually in the last couple of weeks we've settled on the horseshoe inductor to be able to connect the data between the modules and the frame of the device, what we call the endoskeleton, to transmit the data. Now, this is not a trivial problem. We use the MIPI M5 layer 1 protocol, which is a nice modern protocol. It has a variety of different power states, and it has modes from PWM, a low frequency PWM mode, all the way to a 10 gigahertz high-speed Gear 3 mode. And so providing a contactless interconnect that allows efficient data transfer over that full spectrum of frequencies has been a challenge. Now, let me talk a little bit more about what is the electrical architecture of the device. We've embraced the industry standard MIPI Unipro stack that lives layers 2 through 4. At layer 1, as I mentioned, our objective design utilizes the M5 protocol. We have split the design of the Ara platform into 3 design spirals, all of which are conducted quite openly. So we expect to have a developers conference after each one. We had one in April that celebrated the release of the Spiral 1 design, and we document each release in what we call the MDK. And the MDK is an analog, is our hardware analog of the Android SDK. It's the Module Developers Kit. And it documents the platform and allows a module developer without any relationship to Google, without any relationship to any of the partners on the project, to be able to create a module that will work, that is guaranteed or assured to work with the other modules in the device. So compositionally correct. So the Spiral 1 platform demonstrated the Unipro protocol. It also demonstrated a flexible power bus where any module can be a power source, power consumer, or power storage device. It implemented a lot of the network processing in FPGA, so the phone has about 10 minutes of battery life, for those of you who have done FPGA development, and heats up like to a crisp. But nonetheless, it demonstrated the basic technologies, and we believe that it was the first real instantiation of user-serviceable modularity on a device, where the consumer or the user could replace the modules of the phone and make it work. Now, we are currently in the midst of our Spiral 2 development effort, which looks like it'll culminate in the October-November timeframe with a new release of the Module Developers Kit, as well as a prototype device to prove that our platform does in fact work, or is capable of working. We have one of our partners on the project. I mentioned Toshiba as an example. Toshiba is in fact the entity that's developing a set of bridge ASICs that convert legacy protocols, so everything from I2C, USB, SDIO, and bridge them to the Unipro network. And that's pending the native adoption of Unipro in silicon throughout the industrial base. Toshiba is also developing a Unipro switch ASIC. They by no means have exclusivity or monopoly on the Unipro hardware ecosystem. They're just first to the party. But we're actively soliciting new entrants into that ecosystem as well. And so what's displayed here, by the way, are 3 canonical examples of modules: an application processor, and I'll come back and talk more about that in a bit, a display module, which could as well be a camera or something else, and a peripheral module. And we have 2 different flavors of bridges, basically a big bridge that serves APs, displays, and cameras, and a little bridge, or general purpose bridge, that serves some of the lighter weight protocols used in peripheral modules. Now, as soon as we finish Spiral 2, we'll embark on Spiral 3. Now, Spiral 3 is scheduled to run from November through Q1 of 2015. And we anticipate a couple of interesting innovations there. First, it'll be our design spiral that actually implements the pre-production variant of a prototype phone, so something that could plausibly go into a consumer's hands. It'll implement the inductive contactless data interconnect for the first time. And also for the first time, we will demonstrate native Unipro in silicon. So we recently announced a partnership with Rockchip, a chip maker in China that's an ARM licensee. And Rockchip will be making a quad-core A7 processor with a native Unipro general purpose interface, over which all of the display, camera, and other peripheral or other module traffic will go over a single Unipro interface instead of having an assortment of a dozen or more different interfaces. And we're similarly working with with display and camera vendors to try and precipitate and accelerate the native adoption of protocol standards like CSI-3, with storage vendors for protocols like UFS, all of which are Unipro-based protocols, so they can speak natively to the Ara on-device network. Now, I promised to talk a little more about APs. Now, today, in today's world, the AP serves not just as a CPU, not just as a GPU, not just as an ISP, but also as a network hub. There's, as I mentioned, almost a dozen in many of them, and I'm certain that I'm preaching to the choir, different protocols that the AP has to communicate across to the various devices in the mobile phone. Now, the world, according to Project Ara, is that an AP should be just that. It should be an application processor, and its principal function should be to perform computational processing, computation. And the networks leave the network switching to us. So the Unipro switch and a small supervisory controller, which controls the switch and also does the power management functions, is the only thing that lives in the frame of the device. So that is the only core to the system. The AP becomes a module. That module could or could not have the GPU or the camera ISP integrated into it. We take no particular position as the curators of the platform on the correct partitioning of functionality across modules. So we believe that both highly integrated SoCs and disaggregated CPU-only type processing is possible in the Ara platform, and consumers will speak as to what integration versus disaggregation of functionality they prefer. And I've lost the clicker. We have developed a notional design of what an ARM SoC might look like with a general purpose Unipro interface. And basically, and I've mentioned this already, UFS, CSI-3, DSI-2, all of the next generation MIPI protocols are native to Unipro, but we also expect other peripherals that would traditionally speak USB or SDIO to speak over the Unipro controller as well. Now, lastly, you might wonder, what about the software? And in fact, some pretty severe changes are necessary. Android is not designed today for dynamic hardware configurations. And so there are two major categories of modifications that we're making to Android. We're delighted actually to be working with a team from Linaro to make those modifications. We are changing the framework, the Android framework, to be able to support the hot plug of various hardware peripherals. So the ability to have dynamic configurations of the device hardware throughout its operational cycle. And we're also creating at the kernel level, at the Linux kernel level, a set of generic class drivers for Unipro devices, very similar to the way USB device classes are implemented today. We expect that all of the modules in the Ara ecosystem should be either class conforming and therefore fit neatly into one of the Unipro device classes, or non-class conforming, in which case they have to have a user space driver. And the reason for that is done from a security perspective, that we don't want drivers from third-party module developers to live in the kernel. So we're working on a pre-release version of Android L, to make all of these changes. We expect that they will be complete and an end-to-end demonstration in the end of Q1, early Q2 of 2015. And the Android team has committed to then mainlining those changes into a future release of Android. In case you're wondering, I wanted to show you what an Ara module looks like under the hood. This is a Spiral 1 Wi-Fi module. One of those big hunking blocks over there is an FPGA, and so that will obviously be significantly smaller once we move to an ASIC implementation of the bridge. This particular FPGA converts from SDIO to Unipro. Further on the right is the Wi-Fi chipset. You can see there a small antenna connector in the upper right. The pins are the spring pin proxy, if you will, that we're utilizing for now in place of the inductive pads. Once we go to the contactless data interconnect, those will disappear because the inductive pads are just the conductive plating on the bottom of the PCB. So that should free up significant PCB real estate for developer-specific functionality. And in the corner, you see two hand-wound electropermanent magnets. We're working with Foxconn to create production volume, production grade, and production cost version of those electropermanent magnets that look much nicer. And the earlier photo was of a production variant. And then you see lots of discrete components that are needed to actuate the EPMs, do the flexible power management that I described, and all of those will go into a SIP package, so that again, from a developer perspective, the creation of an Ara module should be a relatively straightforward activity, whether you want to do it yourself or pay an ODM or a contract manufacturer to do it. So we've had tremendous enthusiasm for the Ara platform from the developer community. I mentioned our first developers conference, which happened in April, had 6,800 participants in total. We've had about 10,000, a little over 10,000 downloads of the module developers kit. And we had 2,600 applications for dev boards, for developer hardware, for Spiral 1 developer hardware. So we are planning, we don't have specific dates, but we are planning a second developers conference that will run through the second spiral of the platform, and will showcase some of the new Android functionality and Linux kernel functionality for Unipro devices in the December timeframe. And we've also announced a small one and plan to announce a much larger developer prize challenge that basically incentivizes developers to develop for the platform and to enter the Ara ecosystem. If you'd like to have a look at the MDK, there's the URL. It's a simple click-through license, similar to that of the Android SDK. And otherwise, you see it sort of also happens to be the first open reference design for a smartphone that's completely freely available on the internet. So all of the schematics, all of the drawings, and all of the code that we have to date is linked from that URL. And with that, I am finished.
All right, Paul is offered to answer a couple of questions. We're nearly out of time. If anybody's got a question, now is your opportunity. Well, I know we've got some background people.
What about security implications?
The question was, what about security?
Sorry, very poor question.
Implications.
You say you don't want third-party drivers in the system, but if you're in a situation where all of these components share the same memory, there's kind of ways around that anyway.
Yeah, so it is in fact a broad question. One immediate comment is that it's probably practical to share RAM, just from a latency perspective, right? So the Unipro bus can get down to a couple microseconds, but you're still not in the nanosecond territory where you could have RAM that would be external from the CPU on a different module. So most likely the various modules would have, if they need RAM, would have to have some of their own working memory. Now, security is a big topic, obviously, and it's an exciting topic. I think we create all sorts of new attack surfaces, but also all sorts of new flexibility to counter various types of security issues. And so I'm not sure that we have the time for me to do a coherent answer on all of the broad-ranging topics, but in short, we expect a lightweight certification process, but a certification process that at least ensures that modules don't melt or explode or fry your brain before they get into the module marketplace. Now, you can sell out of band, right? So we're not going to prevent developers in the same way that you can get an Android app not from the Play Store. We wouldn't forbid it, right? But in order for us to sell a module, we have to make sure that it's not actively nefarious. We preclude third-party driver functionality living in the kernel, right? So it has to live in user space, so it could only do so much damage. And we're looking at implementing encryption across the bus in order to be able to authenticate and protect the data that's flowing around the bus. So that's a top-level answer. Obviously, devil's in the details.
Say LTE radio and another one.
Yeah. So the question was whether modules can be hot swapped while the device is running. And yes, they can. So I'm remiss in not emphasizing that point. Everything other than the CPU, obviously, which it sort of doesn't make sense necessarily. It's not clear what it means to hot swap a CPU. But aside from that, we expect that most modules, the display is also kind of a hard scenario. But aside from that, most modules would be hot swappable. And that includes, actually, potentially most interestingly, it includes things like batteries and cameras. Right? Those are probably the two most compelling use cases. And in order to hot swap a battery, there's a very small reserve battery that lives in the endoskeleton that provides some seconds of runtime for the device in a low power mode while you swap the primary battery.
All right, thank you very much, Paul, for taking time to come and visit.